Thank you, thank you. It's a pleasure to be here. Thank you to the organizers. It's a real pleasure, in particular, to have an unexpected guest here. Phil Cook is really the world's best at solving large-scale traveling salesman problems. He has written a terrific book on the traveling salesman problem and an absolutely wonderful package for solving large-scale traveling salesman problems called Concord. And I used his Concord package to produce many of these images that you'll see. So TSP here stands for Traveling Salesman Problem, and I'm producing traveling salesman problem-based portraits of knots and links, mathematical knots and links that Rod Neal was talking about yesterday. So let's see. So all of my work really starts with some image. To show you what's going on, I generated a black and white image of a smiley face. And what I'm going to do next is turn this into an instance of the traveling salesman problem. And to do that, we just have to place down a whole bunch of dots. And it's essentially what artists call a stipple drawing. And those dots, when you squint, look very much like the image that we started with. Regions that were dark received a lot of dots. Regions that were bright received considerably less dots. Regions that were completely white received no dots whatsoever. So I have a stipple drawing, a collection of dots. And now I'm going to view these dots as cities. Okay, we're flying up above, and these are cities down below. Alternately, this is a map. Okay, we have 2006 cities. I made this in 2006. Imagine that you're a salesperson who lives in one of these cities. You have to visit each of the other cities once and only once, and then return home. Okay? You're environmentally minded. You don't want to waste fuel. You don't want to waste your time. You don't want to spit out more fuel particles, pollution particles into the atmosphere than is needed. So you want to find the best route through these cities. You want to find the best tour. Okay? Mathematically, well, artistically, what I'm going to be doing is using the least amount of ink to connect all these dots. That's the traveling salesman problem. And when you do that, you end up with a picture that looks like this. Okay? The particular type of traveling salesman problem that you end up with is called a geometric traveling salesman problem, because the lengths of the edge segments, the line segments, are given by the Euclidean distance formula. And it's known that for Euclidean traveling salesman problems, if you look at an optimal solution, you're not going to find any edges crossing. That would be suboptimal. And what that implies is that this resulting object, this tour that the salesman follows, is a Jordan curve, a simple closed curve. It's topologically equivalent to a circle. It divides the plane into two regions, an inside and an outside. And that's something that I take advantage of in my art. I just want to show some of my pieces here. This is one that I did for a conference in Pittsburgh based on portion of Sistine Chapel photography. That, you have the hand of God, the hand of Adam. Are they touching? Well, they're connected through this curve. Okay, for this conference in Pittsburgh, this is the home of Andy Warhol. There's a Warhol museum there. I created a bunch of pieces based on images that Warhol used in his work. This is actually 25,000 cities. This is the path through them. This curve, again, is a simple closed curve. It's just a loop of string. And you might ask, what does the inside of this look like? That's the inside. Okay, if you've used like Microsoft Paint or any sort of paint program, you could take some red paint and click it on a spot that you're sure is on the inside, and then it will fill it in. And if you do that, you get this. So that's what's inside that Campbell soup curve. These next three are all based on familiar images that Warhol used, and I've scaled them so that for each one, the length of the tour is precisely the same. So I could take 180 feet of string and arrange it so that it looks like Marilyn Monroe. Then I could pick off that 180-foot loop of string and rearrange it so it looks like Mao. Then I could pick it off and arrange it so it looks like Warhol. Same length of string in each case. In 2006, I went to a conference in Cork, Ireland, and I did this piece of artwork for them. And I love this one a lot, and it got me obsessed with trying to render knots and links using the traveling salesman problem. What I like about this is if you squint, if you focus, you see that you have a black cord that weaves, it goes over and under, over and under. It's called an alternating knot. Okay? It's a knotted object. It's definitely knotted. But if you focus on the white line, you have the unknot. It's essentially just a circle. Where did the knot go? Now, one thing that's interesting about this is that if I were to color the inside of this curve, the inside of the salesman's tour, I'm not going to get anything that looks interesting. Okay? Well, it might look interesting, but it won't do justice to the original knot. The black cord that forms the knot isn't going to all be uniformly colored red. There are going to be some pieces that are colored red, they're going to be on the inside, and some pieces of that black cord that are going to end up being black, they're going to be on the outside. And it would be great if I could make them all be on the inside or all on the outside. And I've spent a few years working on that, trying to add what you would call side constraints to a traveling salesman problem to make the salesman, when he winds his way through the cities, produce a tour that does justice to the original image. So here we have a two-component link. Each component looks like the other one. They look like fish to me. So we have one fish that's red that's swimming toward the right. We have another fish that's black that's swimming to the left. They're interlaced with each other in a Celtic fashion. And the red stuff is the inside of this white tour. The black stuff is on the outside of that white tour. Again, the white tour is just a loop of string that's been placed down. It doesn't intersect itself at all. Here's another one called outside ring. Why is it called outside ring? Well, because the black ring that looks like it's inside is actually on the outside. You can trace your way out of any spot of black to the outside.
So black is a maze.
You can think of it as a maze, yeah. Now, I want to talk about how I go about doing this sort of thing, give you some details in as much time as I have. I start with an image like this. This is what, the hot flank? No? No.
Yeah.
No. Or this is King Solomon's knot. Some people call this King Solomon's knot. The white. But the white part is the hot flank. Okay?
Nice call.
What was that? Okay.
White bit.
Well, again, I start by laying down some dots. I produce a stipple drawing of it. Now, if I use Bill Cook's Concord code, and I find the optimal tour through these 500 dots, Bill's code does this quite nicely, I end up with something that looks pretty. Simple closed curve through the points. If I color the inside green, well, it doesn't do justice to the original. The original picture that I had has two components. One that goes from the lower left to the upper right, and one goes from the upper left to the lower right. And if I were to color this, I would like to give each of those components a different color. So when I'm using blue and green, I really like one of those to be blue, entirely blue, and one to be entirely green. Okay, so this doesn't do it for me. Maybe you like it, but it doesn't do it for me. So you need to force the salesman, when he's traveling through the cities, to produce a tour that behaves itself. Okay? Now there's four what I call city-free regions here. I've labeled them A, B, C, and D. The problem is I would really like A and B to be on opposite sides of the tour. I would like B and C to be on opposite sides. That is the case. I would like C and D to be on opposite sides. They're not. A and D are on opposite sides, which is good. If I use side constraints, I can force the salesman to travel through the cities in this way, which looks a lot better. Okay, now how do you go about solving a traveling salesman problem? Bill, this is from your book. Thank you. This is an example of a small-scale traveling salesman problem. It's a 8th Judicial Circuit traveled by Abraham Lincoln back in 1850. This is the route that he took when he traveled from town to town as a lawyer. You see that there are, I think there were 13 cities here. I've labeled them, no, 14 cities, labeled them in alphabetical order. Okay, so 14 is Collier bomb building. This is the route that Lincoln followed. Okay? Now, when you're solving the traveling salesman problem using a technique called integer programming, you need what are called decision variables, and we use binary variables that take on two values, 0 or 1. For each edge, we have one of these variables, for each possible edge, and we set the variable equal to 1 if we actually do use that edge in the tour, if a line segment is drawn along that edge. For example, Lincoln went from city 3 to city 8, or from city 8 to city 3, one of the two. Cities 3 and 8 were visited consecutively. So the variable x38 is set equal to 1. x911 is set equal to 1, because cities 9 and 11 are visited consecutively. Note that x12 is 0. Why? Cities 1 and 2 weren't visited consecutively on the tour. So you can, this is sort of a code where you can rewrite the information that's contained in the picture that's the tour in a different format, just using zeros and ones, which ends up being particularly convenient when you're writing it down in mathematical form. You can get a linear expression that gives you the total length of the tour. You just add up over all edges the cost of the edge times the variable. If the variable is 0, that cost is wiped out. It's not added into the expression. If the variable is 1, then that cost is added in. So this computes the total length of the tour. Now you need to impose constraints on your variables. If Lincoln went to a travel agent and said, please construct me a tour, and the travel agent gave Mr. Lincoln this, he would say, I can't do this. Okay, I cannot follow this. This isn't a tour. Okay, and the problem is, well, there's several problems. City 9 only has one edge coming out of it. Same with City 8, City 11. City 2 has 3 edges incident to it. In a tour, you need each city to have, in graph year terms, degree 2. You need a way in and a way out. So we have constraints that do that. The other thing we need to do is have constraints that eliminate what are called subtours. If Lincoln went to his travel agent and the travel agent gave him this, he'd say, I can't do this. Now, I might be a great man, but I don't know how to teleport. And that's what this would require. You go from city 1 to 5 to 9, how do you get over to the other side? You would have to teleport, and that's not allowed. Well, we can prohibit that by using constraints of this form. And we end up with what's known as the Danzig, Fulkerson, Johnson formulation of the traveling salesman problem, which is, what, about 52 years old? Is that right? Yeah, around there. Okay? And this formulation is really at the heart of the methods used in Bill Cook's Concord Code. There's a heck of a lot of stuff on top of it that makes it work for very large-scale problems. But this idea is really at the core of the onion. Okay? Now, just to give you an example how this would work, how you would go about doing this. Oh, one thing I should say. How big a problem is this? Well, if you have n cities, n dots, then the total number of variables that you have is n choose 2. Okay, so, on the order of n squared. The number of constraints that say that each city must be touched twice, well, you have exactly n of them. How many constraints are there that are subtour constraints that eliminate subtours? Well, it's on the order of 2 to the n, an exponential number of them. So this approach, as written, you couldn't just apply by typing all these constraints into the computer. You'd end up exhausting your memory very quickly. So the strategy is to use these subtour constraints just as needed. When a subtour pops up, you stamp it out with one of these subtour elimination constraints. So here's an example, a test piece of TSPR. We've got 2 city-free regions, A and B. There's a total of 50 cities. Okay, if we don't worry about subtours at all, and just use the degree constraints, we end up with this. We end up with a total of, I believe, 6 subtours. How can we eliminate them? Well, I'll focus on the triangle that connects cities 13, 19, and 25. If we add this constraint in, it says that x13, 19, x13, 25, x19, 25 has to be strictly less than 3. What we're saying is we can use at most 2 of the edges to form that triangle. If we use at most 2 of those edges, we're not going to get that triangle. We're going to get something else. We're not ruling out any tour. We're just ruling out that triangle. And similar constraints can be used to eliminate the other subtours. So if you keep doing this in stages, you eventually end up with the tour. You haven't ruled out any tours by adding these constraints, so this must be the optimal tour. Now, how could I force, let's say, cities A and B to be on opposite sides of the tour? Okay, are we convinced that they're on opposite sides of the tour?
No, they're not. They're on the same side.
Right, they're not. They're on the same side. How can we convince ourselves that they're on the same side? Well, there's two ways. You can find a route that goes from A to B, like a maze, or you can look at this line and see how many edges of the tour it crosses. And since it crosses an even number, they must be on the same side of the tour. So essentially what I did was I figured out a way to add some additional binary variables and some additional constraints that would allow me to force A and B to be on the same side of the tour. Basic idea is this. I define a set chi of L comma L sub A comma B. L sub A comma B is some straight line that connects city-free region A to city-free region B, and chi is the set of all edges that cross that line. Okay, so you figure I would look at all the different edges that cross that line. Okay, and the observation is a simple one. It's what I just mentioned, that A and B lie on the same side of the tour if the sum of all those edges ends up being even. And how can I enforce that? Well, if you're teaching a discrete math class, how do you get across to students the idea that a certain quantity is even? Well, you tell them to write it as 2 times some integer. So I'm just introducing an integer, YAB, and forcing that sum that I want to be even to be twice that. And if I want them to be on opposite sides of the tour, I do the same thing. And I just force that sum to be 2 times that new variable y plus 1. Very simple idea, adding these side constraints. And here's just some designs that I've created using this. In addition to what I've mentioned already, I've added some constraints that force symmetry. When I laid down the dots, I forced there to be, actually in this case, 6-fold rotational symmetry. And when I solved the traveling salesman problem, I added in constraints that say that if I use one particular edge, I also have to use the rotated versions of that edge. If I don't use an edge, then I don't use the rotated versions. But those constraints make the problem actually easier because they cut down on really essentially the number of variables that are used. If I'm dealing with 3-fold rotational symmetry, I now have 1/3 the number of decision variables than I had before, and I can solve the problem much easier than I did. This actually, some of these examples actually have more symmetry than is immediately apparent. This is one of my favorite designs that I've done. You can see that it has 3-fold rotational symmetry, but actually the dot pattern, the stippling, had 6-fold rotational symmetry. And you can see that there are certain motifs here. There's like things that I think of as like the head of a snake. It looks sort of like the head of a snake. Let's see if I can. Is this appearing? Yeah. I think of this piece here as the head of a snake. Here's the body of the snake, so it curves around, and there's the head. So that's a green snake head. And if you go 60 degrees, you see a blue snake head on a green background. And it's over here. Blue snake head on a green background. Then we have a green snake on a blue background, blue snake. So you get this sort of color change symmetry that's happening in the middle of the picture. And that also happened in this one as well. There's this nice color change symmetry. So just different examples. This is a couple animations strung together that actually do a good job of convincing people that this tour doesn't cross itself at all. And then it fills in the color. So while I'm doing that, I can say that I've also done some of these in solid form by having a laser cut out the path. So let's see. This one here is the design that we saw before. And I had it done in black acrylic and also in a light colored acrylic. And what's neat about it is just 2 pieces. The whole idea is that this curve, this path that the salesman follows, is a simple closed curve. It cuts the plane into 2 pieces, an inside and an outside. So this must be just 2 pieces. And I can carefully do that. I have these 2 pieces. And I've been trying to get them in a more solid material. This is stainless steel and copper. You can't use a laser cutter too easily to cut metal because you end up spot welding the metal to whatever is below it. So I end up having to use a water jet cutter. It shoots a very thin stream of water at very high speeds, and you end up with something like that you can take out.
Can you hold that in front of the white screen?
Hold it in front of the projector so we can see the shadow.
And the other one next to it. Step back. Yep.
There you go.
And I found it just amazing to try and put some of these things into a solid form. I found, in the last few years, after I started doing this sort of thing, that you have this great pleasure as somebody doing artwork in taking something that originally lived on the computer screen and putting it first in print. I tend to print on canvas and then laminate the canvas, and just seeing that is just a huge step above seeing it on the computer screen. And now seeing them in solid form where you can actually just manipulate them, and you get the satisfaction of having these 2 pieces just fit together perfectly, is just wonderful. And another thing that's wonderful is I was forced in doing all these pieces to come up against the constraints that are imposed by the physical materials. And just having to work with that is it's a wonderful thing. It's something that's hard and frustrating at times, but it's a wonderful thing to do that. So even though I start in the virtual world, my goal is to get things in the more physical world.
So if you water jet cut a stone with it?
You could, yeah.
Did you?
No.
You can.
Okay, right. I don't have as much access to this equipment as I would like. I'd love to spend all day cutting stuff out and putting it together, but I don't. It's expensive.
Bob, I also noticed your curves are all C0. They're not differentiable.
Well, there's some smooth ones. So, I like symmetry. You have this color change symmetry going on. Here, I've got a smooth version of it. So instead of just connecting the points via straight line segments, you can use Bezier curves to smooth things out. And here you don't actually see the path taken by the salesman. The path taken by the salesman is the border between these 2.
Now this one doesn't have continuous derivative.
These are all based on the same, these next 3 are all based on the same set of points, 3,000 something points. If you connect them in a certain order, you can get that. If you connect them in a different order, you get that. If you connect them in a different order, you get that. It's continuous but not different. Okay, this is like the one that I showed you here, but this is done out of 1/4 inch thick brass, 1/4 inch thick stainless steel, and then you swap the pieces. You get that.
You get a twofer.
You get a twofer. Actually, these you don't get a twofer because if you're cutting 1/4 inch thick metal with a water jet cutter, the thickness of the line is quite wide. So they had to cut along the inside of the curve and then cut along the outside of the curve to form these. So there was some waste. If you just cut the curve, you end up with a wider curve. But I actually like having that thick line there. There's more play in the actual object in the end, but having that thick line as sort of the third element works very well for me, personally. And then one other thing I did was I kept the 1/4 inch thick interior and put in an 1/8 inch thick exterior that we see there. So they're both stainless steel, it's just that the inner piece is twice as thick as the outer piece, and you get some nice shadows with that. I have some references. I've already mentioned Bill Cook. I should have had him on the slides here. The work that's done is described in several papers. A big contributor to all this stuff is a guy named Craig Kaplan, who teaches at the University of Waterloo, a computer graphics guy. He helped me figure out, suggested the key idea for placing the dots, and I didn't talk about that aspect here, but you can read about that in the Bridges 2005 paper. I want to recommend quite highly any of you to go to Bridges, the Bridges conferences. Bridges is a conference that brings together math and art people. It's held once a year, usually in late July, early August. This year it's going to be in Banff. Maybe you're not going to go this year, but think about going in the future. Another thing that I would like you to think about is possibly submitting a piece to a journal that's come out in the past couple of years, the Journal of Mathematics and the Arts. I'm on the editorial board. Venus is on the editorial board. We are looking for articles. We can get something in print rather quickly. There have been really nice articles that have come out in the first 2 years of this journal's life. If you haven't heard of the journal, check it out. Google Journal of Mathematics and the Arts. Email me. I will do what I can to help you if you have an idea to get it so that it ends up being submitted there, in submitted form. Okay? All right. This one was just done around, it was mapped using stereographic projection around the hemisphere. So I'm done with a few minutes to start. Thank you.
You started with a picture and you turned it into points,
Yes.
smiley face in the line.
Yeah.
Have you iterated that process and have you found any interesting fixed points? Fixed images?
So you mean you take an image, turn it into points, and then turn that image into points?
Right.
Well, the fixed points then would be you have a set of 2,000 points. If you stipple that, I think you're going to end up with just that same series of points.
Do you think you're right?
Well, the way
You started with the smiley face,
Yeah.
and you got the next stage which resembled the smiley face.
right.
Now that's a picture. If you started taking points of that and then doing the process again, would you get exactly the same thing, or would you get a second generation of
The
smiley
process
face?
that's used to place down the points is, I like to use a process that has some randomness in it. So if I'm doing one of these, I like to have many different versions of this, and then pick the one that pleases me most aesthetically. So by virtue of the randomness involved in this process, I probably would end up with something that looked a little different. But from a distance, it wouldn't look any different at all. So I don't know if iteration really is, at least thinking about it right now, is something that would be terribly interesting. But I've said things like that in the past. People have suggested things. Somebody suggested, well, could you do this in color? And I said, oh, no, absolutely not. But you actually can. You could do separate tours for red, blue, and green, and then interlace them. And it actually ends up, it's kind of hard to do, but I just have crude-looking prototypes. But it's something that's definitely possible. So I don't want to say that your idea is, not a good one at all. It could end up being, a great idea. I just don't see how to do it right now. Huh?
I do have a traveling salesman program and problem in 3 dimensions.
Mm-hmm.
And there are space curves.
Space on curves.
Well, there's space curves.
Space curves. Yeah, you can do this in 3 dimensions.
So you take this say, body.
And yeah, and you find a wire that, a path through space. So essentially a loop.
Have you done the traveling salesman?
I've done small versions of that, just prototypes, nothing that is worth showing. But going into 3 dimensions is definitely something I want to do.
Good.
Go ahead. You go first.
Have you tried taking the segments from Maryland through Mao through Andy and putting them, say, in an interpolator like an Illustrator?
Trying to morph from one to the other?
And get a sequence of morphs, yeah.
I haven't tried that.
Or even a 3-dimensional model where the morphs are stacked.
No, I haven't tried that. I would love to be able to morph from one to the other. What these are essentially is one way of looking at them is they're non-convex polygons. These objects, they're linkages, and Eric Demain showed that you can convexify any non-convex linkage. And it'd be great to see an animation where you took Maryland and then turned it into essentially a big circle or something like a circle, big convex polygon, and then it folded back in to form out, then it folded out, and then it folded back in to form Warhol. I've tried to get Eric interested.
How are your data arranged? What form is your picture?
Well, it's just a collection of points with their coordinates, and then an order in which you...
No, the picture is either a PDF or an EPS or...
No, the original picture? The original picture I convert to PGM format, which just has an integer value for each pixel between 0 and 255. 0 is black, 255 is white.
So it's not a vector based, right?
No, not the original picture. No, not at all. Yeah.
I like your art very much. It's really interesting. I mean, definitely it's a way of making the TSP, more understandable to the general audience.
Well, I actually think the TSP is a fairly simple problem that even small age school kids can figure out. Everybody does problems with the TSP on a routine basis.
Not everybody knows.
Well, not everybody knows the name and knows how hard it gets when the number of cities gets larger. But everybody has to run errands, and they figure out what order I want to do these errands in. And they're solving TSP, small scale ones, as they go.
The question actually I have, my actual question is, in all the artwork that you created, you use the optimal algorithm?
I should say that solving a large-scale problem to optimality is very, very hard. For a lot of the ones that I showed originally, the Maryland, the Mao, those, the soup cans, I did not attempt to find an optimal solution.
Okay.
I used something called a Lynn-Kernighan heuristic that's part of the Concord package
to
find a very good tour. For some of these knot-based ones, I actually wrote some of my own code, and because these are smaller problems in size, particularly when you take into account the symmetry, I am able to find optimal solutions to those.
Actually, you already did it, but I asked, did you experiment with weights on the points and with Steiner minimal trees?
No, I haven't looked at the Steiner minimum tree. I have looked at minimum spanning tree, connect the points using a minimum spanning tree, and that leads to interesting looking.
It's also interesting.
Okay.
Thank you.
Sure.
I was actually curious, as a software developer, did you ever imagine a use like this of your software?
No.
Cool.
Going back to this, long time ago, I used to be interested in, I never did anything with computation of traveling salesman or combinatorial problems, but I was interested in the perfect matching problem.
Mm-hmm.
And even a more generalization of that, which I actually had a PhD student, K-perfect matching, where trying to, say, cover a bunch of points with an optimal tools of size K,
Okay.
partitioning it. And we had some family of good heuristics, actually.
So
Didn't guarantee that they
perfect
could not be
matching
all non-intersecting. But those kind of things may also give, perfect matching problem may also give rise to, which is
a related project that I've been doing is looking at graph coloring. So you take a graph, vertices and edges, and you had some graphs, and you were coloring them so that Radmila had some graphs where vertices that were connected by an edge had to get different colors. Well, if you start with, let's say, a grid of squares, you could view each of those squares as a vertex in a graph, and each square will have 4 neighbors, north, south, east, and west, and you want to color that checkerboard, that grid of squares in with, let's say, 6 shades of gray, so that number 1, the resulting collection of squares shaded looks like some desired picture, and number 2, that this graph coloring constraint has been satisfied. The neighboring squares have to receive different shades. I've been doing some work with that, and that's a lot of fun. So basically, the theme of what I do is to take classical optimization problems and try and view them from an artistic side. Use them to try and create visual imagery.
I want to add one more comment, actually, that it is somewhat ironic that while we can solve very large traveling salesman problems, you know, like some of these were, how large, how many?
25,000.
25,000. We do not seem to be able to solve very large degree polynomials, you know, solving very large degree polynomials. I mean, if I want to do a polynomiography of a polynomial of degree 1,000, you know, it's a tough job.
Well, certainly to find an optimal
So
solution.
a polynomial problem, a polynomially solvable problem, in a sense, is in some sense is harder than solving a NP-hard problem.
Well,
you know,
I don't know about that.
because of numerical problems that come into the picture.
Sure. But again, the 25,000 city SUPCAN one was a tour that wasn't necessarily optimal. It's very likely that it wasn't optimal. It still looks good, but it's not optimal in terms of total distance traveled.
I mean, several of our larger problems took over 100 years to solve. We were done in parallel.
Sorry?
Several of the large problems, TSP problems we solved, took over 100 years of computing time to solve. We just split it up over workstations.
Yeah, about a year and a half ago, Bill asked me to produce a traveling salesman portrait of a gentleman named Ralph Gomery, who's one of the fathers of the field of integer programming. And that involved something like 8,000 cities. And I produced a tour using, you know, a heuristic, so it wasn't necessarily the optimal tour. And then Bill wanted to give to Ralph, you know, the optimal tour. And it took Bill's computer something like 32 CPU days to find the optimal tour. So, you know, a considerable amount of computational effort is required to find the optimal. You know, you can't put it in a plug-in. You know, have people wait 32 years, obviously. Well, thank you.